Good evening, ladies and gentlemen. My name is Terry Bristol, and I'm the president of the Institute for Science, Engineering, and Public Policy. It's my great pleasure to welcome you this evening to a special public presentation by Dr. Stephen Hawking. Before OPB's Maynard introduces Dr. Hawking, I want to take a moment to thank the co-sponsors and underwriters that helped make tonight's event possible. The main co-sponsor is Intel, and jointly Intel Foundation and the Supercomputer Systems Division of Intel Corporation. Although we've been talking to Dr. Hawking's office for roughly 2.5 years about the possibility of having him come to Oregon, we actually fixed a definite date only 60 days ago. And so I want to express my appreciation to the people at Intel for responding with the needed funding underwriting for within literally a few days. Made all the difference. In particular, I want to single out Bob French, who's the head of public affairs at Intel, who championed this project through Intel. Additional underwriting was provided by Oregon Public Broadcasting, engineering firm CH2M Hill, the University of Portland, the high-tech PR firm Wagner Edstrom, and Portland State University. And special thanks to the Heathman Hotel, where Dr. Hawking and his support staff are staying. And I might add that the Heathman Hotel is highly wheelchair accessible. Indeed, Dr. Hawking met this afternoon with 25 wheelchair students from the Portland Public Schools for about an hour in the Broadway room at the Heathman. So we had 25 wheelchairs go in there, and it worked really great. Appreciation to Steve Carlson, the science specialist at the Portland Public Schools, for spearheading the arrangements for that meeting. For those of you who haven't been to one of Portland Science Technology Society lectures before, there's information about the next 3 lectures inside cover of your program. So if you want to come to some of those, I think you'll find those very enjoyable. There's also inside your program is a card, and on that card there's this thing says question for Dr. Hawking, so you can fill out a question card, and the ushers at the end of the formal talk will collect those and bring those down. And also on that, yeah, so he anyway, I'll talk more about how we're going to do the questions. He said, could we limit it to 5 questions, which we will do. And it takes him a couple of minutes to type in the answer, and so we just talk amongst ourselves while we're waiting, and then he answers the question. We did it works very well this afternoon. Also on those cards, then, I was going to tell you just technically how he's doing some of this tonight is that what he's going to do is come out and he's going to feeds sentence by sentence what he's put in for the talk tonight from his computer. So that's how it's going to operate. We're going to wire him in here and be out here, and his assistant will help him. On those cards, there's also a place where you can put your name and address, so that next time we do something like this, or more information on the series, we can put you on the mailing list and get that to you. And just to tantalize you a little bit, we've been talking, it's possible that within the next couple of months, Jacques Cousteau, that's the old guy, not his son, 83-year-old, I believe you can't get him as a speaker normally, but he's got this thing that he started, you may have seen it on television, a petition for the rights of future generations. And he's going all over the world to get signatures. He wants to get 20 million signatures and submit this to the United Nations. So it's sort of like the Helsinki Accords on human rights or something. It's really, I think, a nice idea. And we were talking to him about helping him with a kind of a Northwest leg of promoting that. So possibly, I don't know if it's going to happen, but we'll see. His son, Jean-Michel, we just confirmed is going to be the first speaker in next year's series, which will be in October of '92. So that's one encouragement to fill out the cards. The other is we do this little game, which is Stephen actually does autographs, not a lot, but he has a little thumb deal that he does. And so I've got 6 copies of A Brief History of Time, which he's going to autograph for me, and then we're going to do a lottery thing off these cards. So if you fill out the card, put your name and address on it, and either we'll collect it or you can drop it you know, outside on one of the tables, and we'll pick them up, and then we'll do a little lottery drawing in the next week or two, send you one of the 6 winners will get one of those books. Isn't that clever? I hope all of you had an opportunity to read Dr. Hawking's article in the Oregonian on Wednesday. It's reprinted actually in your program with a title. It had different titles in your program. It's Awakening the Scientist in All of Us. And in that he postulates that television is the medium of choice to educate the public about scientific and environmental issues because of its ability to reach mass audiences. So it's especially appropriate that Oregon Public Broadcasting, with its strong track record of scientific and environmental programs, has been a major sponsor of the Science Technology Society Lectures series since we started this 4 years ago. It's a pleasure then to introduce now Maynard Orme, President and CEO of Oregon Public Broadcasting, who will introduce Dr. Hawking.
Thanks, Terry. Thank you. Thank you very much, Terry, and good evening. Oregon Public Broadcasting is extremely proud to have served as co-sponsor of the Science and Technology Lecture Series since its inception 4 years ago. It's a wonderful addition to the intellectual life of this community. Tonight is clearly a high point in this ongoing series of outstanding speakers that Terry Bristol and Suzanne Graham have brought here. It is a distinct honor to introduce tonight's speaker. One of our previous speakers, Carl Sagan, wrote of his first encounter with Stephen Hawking. Quote, "In the spring of 1974, about 2 years before the Viking spacecraft landed on Mars, I was at a meeting in England sponsored by the Royal Society of London to explore the question of how to search for extraterrestrial life. During a coffee break, I noticed that a much larger meeting was being held in the adjacent hall, which, out of curiosity, I entered. I soon realized that I was witnessing an ancient rite, the investiture of new fellows into the Royal Society, one of the most ancient scholarly organizations on the planet. In the front row, a young man in a wheelchair was, very slowly, signing his name in a book that bore on its earliest pages the signature of Isaac Newton. When at last he finished, there was a stirring ovation. Stephen Hawking was a legend even then. Professor Hawking has earned an international reputation as the most brilliant theoretical physicist since Einstein. He is the author of the landmark book, A Brief History of Time, probably the most widely read popularization of theoretical work about quantum mechanics and general relativity ever written. The book was on the New York Times bestseller list for nearly 2 years. He has been the Lucasian Professor of Mathematics at Cambridge University since 1979, and some of you know that's the same professorship that was held by Sir Isaac Newton. Born 50 years ago on January 8th, exactly 350 years after the death of Galileo, as he's quick to point out, he has pursued a distinguished career as a great scientist and a great teacher. His curriculum vitae includes scores of outstanding achievements in research and scientific discovery. Stephen Hawking's personal autobiographical sketch is printed in your program. From it you can derive that besides being possessed of a colossal intellect, he is also witty and self-effacing. You must take the time to read Dr. Hawking's biography in the program for yourself, but right now let me read to you my favorite sentence to illustrate the point. Hawking writes, "I was a fairly normal small boy, slow to learn to read, and very interested in how things worked. I was never more than about halfway up the class at school. Parentheses, it was a very bright class, end of parentheses. When I was 12, one of my friends bet another friend a bag of sweets that I would never come to anything. I don't know if this bet was ever settled, and if so, which way it was decided." That Hawking is so dedicated to sharing his concepts, not just with a small elite body of fellow scholars, but with a far broader audience of the lay public curious about their universe, is further evidence of his profound genius and his incredible gifts as a communicator. His determination to conquer his physical challenges, unimaginable to most of us, places him in a category that is absolutely unique. Today I observed at first hand as he communicated with a group of handicapped students from Portland Public Schools and answered their question. Dr. Hawking's topic tonight is entitled Black Holes and Baby Universes. He will be accompanied on stage by Jonathan Brenchley, his graduate assistant. Ladies and gentlemen, I am truly honored to present our most distinguished speaker, Dr. Stephen W. Hawking.
Can you hear me? This may be the first time you have been addressed by a real computer. You may have seen science fiction films like 2001 in which there were computers that spoke. But these films are really cheats. The computer parts were spoken by humans. The reason was that computerized speech synthesizers were not sufficiently good to be used in films or TV programs. But the speech synthesizer is a great improvement. It varies the intonation and gives me a voice that sounds almost human instead of like a Dalek. The only trouble is that it gives me an accent that has been variously described as American, Scandinavian, or Irish. The speech synthesizer is controlled by a small portable computer on the back of the wheelchair. The screen of the computer has been taken off and mounted on the arm of the wheelchair. On the screen, I have a menu which I can scan by pressing a switch in my hand. In this way, I can select words which are printed out on the lower part of the screen. When I have written what I want, I can send it to the speech synthesizer. I can write scientific papers on this system. I write equations in words, alpha plus beta over 2 equals gamma. I have a program called Tech, which translates the equations into symbols and sets the paper in appropriate type. I have also used it to write a popular book, which is being translated into 25 languages. I realized it was going to be a success when I sold the rights in Serbo-Croat. Now for my lecture. I will talk about black holes, which ain't as black as they are painted. Instead, I shall show that they can shine white hot. And they can be the proud parents of little baby universes. Falling into a black hole has become one of the horrors of science fiction. In fact, black holes can now be said to be really matters of science fact, rather than science fiction. As I shall describe, there are good reasons for predicting that black holes should exist. And the observational evidence points strongly to the presence of a number of black holes in our own galaxy and more in other galaxies. Of course, where the science fiction writers really go to town is on what happens if you do fall in a black hole. A common suggestion is that, if the black hole is rotating, you can fall through a little hole in space-time and out into another region of the universe. This obviously raises great possibilities for space travel. Indeed, we need something like this if travel to other stars, let alone other galaxies, is to be a practical proposition in the future. Otherwise, the fact that nothing can travel faster than light means that the round trip to the nearest star would take at least 8 years. So much for a weekend break on Alpha Centauri. On the other hand, if one could pass through a black hole, one might re-emerge anywhere in the universe. Quite how you choose your destination is not clear. You might set out for a holiday in Virgo and end up in the Crab Nebula. I'm sorry to disappoint prospective galactic tourists, but this scenario doesn't work. If you jump into a black hole, you will get torn apart and crushed out of existence. However, there is a sense in which the particles that make up your body do carry on into another universe. I don't know if it would be much consolation to someone being made into spaghetti in a black hole to know that his particles might survive. Despite the slightly flippant tone I have adopted, this talk will be based on hard science. Most of what I shall say is now agreed by other scientists working in this field, though this acceptance has come only fairly recently. The last part of the lecture, however, is based on very recent work, on which there is, as yet, no general consensus. But this work is arousing great interest and excitement. Although the concept of what we now call a black hole goes back more than 200 years, the name black hole was introduced only in 1967 by the American physicist John Wheeler. It was a stroke of genius. The name ensured that black holes entered the mythology of science fiction. It also stimulated scientific research by providing a definite name for something that, previously, had not had a satisfactory title. The importance, in science, of a good name should not be underestimated. Black holes were first thought about in Cambridge. A fellow of Queen's College, John Mitchell, wrote a paper about them in the Philosophical Transactions of the Royal Society in 1783. His idea was this. Suppose you fire a cannonball vertically upwards from the surface of the Earth. As it goes up, it will be slowed down by the effect of gravity. Eventually, it will stop going up and will fall back to Earth. However, if it had more than a certain critical speed, it would never stop and fall back, but would continue to move away. This critical speed is called the escape velocity. It is about 7 miles a second for the Earth, and about 100 miles a second for the Sun. Both of these velocities are higher than the speed of a real cannonball, but they are much smaller than the velocity of light, which is 186,000 miles a second. This means that gravity doesn't have much effect on light, and light can escape without difficulty from the Earth or the Sun. However, Mitchell reasoned that it would be possible to have a star that was sufficiently massive and sufficiently small in size that its escape velocity would be greater than the velocity of light. We would not be able to see such a star because light from its surface would not reach us, but would be dragged back by its gravitational field. However, we might be able to detect the presence of the star by the effect that its gravitational field would have on nearby matter. It is not really consistent to treat light like cannonballs. According to an experiment carried out in 1897, light always travels at the same, constant, velocity. So it is difficult to see how gravity can cause light to fall back. This problem remained until 1915, when Einstein formulated the general theory of relativity. Even so, the implications of this theory for old stars and other massive bodies were not generally realized until the 1960s. According to general relativity, space and time together can be regarded as forming a four-dimensional space, called spacetime. This space is not flat, but it is distorted or curved by the matter and energy in it. Objects try to move on straight lines through spacetime, but because it is curved, they move on paths, which are the nearest thing to a straight line in a curved space. Thus, the Earth tries to move on a straight line, but because spacetime is bent by the mass of the Sun, it follows a spiral path, going in a circle round the Sun, while advancing in time. Similarly, light tries to move on a straight line, but because spacetime is curved, it appears to follow a path that is bent. We can actually observe this bending of light during an eclipse. The moon blocks out the sun and allows us to observe stars that are in almost the same direction as the sun. We find that the stars appear to be in slightly different positions, because the light from them is bent by the curved spacetime near the Sun. In the case of light passing near the Sun, the bending is very small. However, if the Sun were to shrink until it was only a few miles across, the bending would be so great that light leaving the Sun would not get away, but would be dragged back by the gravitational field. According to the theory of relativity, nothing can travel faster than light. So there would be a region from which it would be impossible for anything to escape. This region is called a black hole. Its boundary is called the event horizon. It is formed by the light that just fails to get away from the black hole, but stays hovering on the edge. It might sound ridiculous to suggest that the Sun could shrink to being only a few miles across. One might think that matter could not be compressed that far. But it turns out that it can. The Sun is the size it is because it is so hot. It is burning hydrogen into helium like a controlled H-bomb. The heat released in this process generates a pressure that enables the Sun to resist the attraction of its own gravity, which is trying to make it smaller. Eventually, however, the Sun will run out of nuclear fuel. This will not happen for about another 5 billion years, so there's no great rush to book your flight to another star. However, more massive stars will burn up their fuel much more rapidly. When they finish their fuel, they will start to lose heat and to contract. If they are less than about twice the mass of the Sun, they will eventually stop contracting and will settle down to a stable state. This state can be what is called a white dwarf. These have radii of a few thousand miles and densities of hundreds of tons per cubic inch. Or it can be a neutron star. These have a radius of about 10 miles and densities of millions of tons per cubic inch. We observe large numbers of white dwarfs in our immediate neighborhood in the galaxy. Neutron stars, however, were not observed until 1967, when Jocelyn Bell and Tony Hewish at Cambridge discovered objects called pulsars, which were emitting regular pulses of radio waves. At first, they wondered whether they had made contact with an alien civilization. Indeed, I remember that the seminar room, in which they announced their discovery, was decorated with figures of little green men. In the end, however, they, and everyone else, came to the less romantic conclusion that they were rotating neutron stars. This was bad news for writers of space westerns, but good news for the small number of us who believed in black holes at that time. If stars could shrink as small as 10 or 20 miles across to become neutron stars, one might expect that other stars could shrink even further to become black holes. A star with a mass more than about twice that of the Sun cannot settle down as a white dwarf or neutron star. In some cases, the star may explode and throw off enough matter to bring its mass below the limit. But this won't happen in all cases. Some stars will shrink so small that their gravitational fields will bend light so much that it comes back towards the star. No further light or anything else will be able to escape. The stars will have become black holes. We now have fairly good observational evidence for a number of black holes. One of the best cases is Cygnus X1. This is a system consisting of a normal star orbiting around an unseen companion. Matter seems to be being blown off the normal star and falling on the companion. As it falls towards the companion, it develops a spiral motion, like water running out of a bath. It will get very hot and will give off the X-rays that are observed. The unseen companion must be very small, a white dwarf, neutron star, or black hole. However, one can show that the mass of the companion must be at least 6 times that of the Sun. This is too much for it to be a white dwarf or a neutron star. So, it has to be a black hole. I once bet Kip Thorne of the California Institute of Technology that Cygnus X1 does not contain a black hole. This was not because I didn't believe that there really was a black hole in Cygnus X1. Rather, it was an insurance policy. I had done a lot of work on black holes, and it all would have been wasted if it had turned out that black holes didn't exist. But then, at least, I would have had the consolation of winning my bet. However, I now consider the evidence for black holes so compelling that I have conceded the bet. I have given Kip Thorne a subscription to Penthouse. The laws of physics are time-symmetric. So, if there are objects, called black holes, which things can fall into, but not get out, there ought to be other objects that things can come out of, but not fall into. One could call these white holes. One might speculate that one could jump into a black hole in one place and come out of a white hole in another. This would be the ideal method of long-distance space travel mentioned earlier. All you would need would be to find a nearby black hole. At first, this form of space travel seemed possible. There are solutions of Einstein's general theory of relativity in which it is possible to fall into a black hole and come out of a white hole. However, later work showed that these solutions were all very unstable. The slightest disturbance, such as the presence of a spaceship, would destroy the wormhole, or passage, leading from the black hole to the white hole. The spaceship would be torn apart by infinitely strong forces. It would be like going over Niagara in a barrel. After that, it seemed hopeless. Black holes might be useful for getting rid of garbage, or even some of one's friends. But they were a country from which no traveler returns. However, everything I have been saying so far has been based on calculations using Einstein's general theory of relativity. This theory is in excellent agreement with all the observations we have made. But we know it cannot be quite right, because it doesn't incorporate the uncertainty principle of quantum mechanics. The uncertainty principle says that particles cannot have both a well-defined position and a well-defined velocity. The more precisely you measure the position of a particle, the less precisely you can measure its velocity, and vice versa. In 1973, I started investigating what difference the uncertainty principle would make to black holes. To my great surprise, and that of everyone else, I found that it meant that black holes are not completely black. They would be sending out radiation and particles at a steady rate. My results were received with general disbelief when I announced them at a conference near Oxford. The chairman of the session said they were nonsense and wrote a paper saying so. However, when other people repeated my calculations, they found the same effect. So, in the end, even the chairman agreed I was right. Please wait while I load the rest of my lecture. How can radiation escape from the gravitational field of a black hole? The answer is, the uncertainty principle allows particles to travel faster than light for a small distance. If a particle is confined to a certain region, like a black hole, there has to be a bit of uncertainty in its speed. So it is possible for the speed of the particle to be greater than the speed of light. This would enable the particle to get out through the event horizon and escape from the black hole. The smaller the black hole, the greater will be the uncertainty in the speed of the particle. Thus, particles in radiation will leap more rapidly out of a small black hole than out of a large black hole. For a black hole of the mass of the Sun, the rate of emission is so low, it cannot be measured. But there may be much smaller black holes, which may have been formed in the very early universe. If there were enough of these very small black holes, we could detect the radiation they gave out. People have looked for radiation from little black holes, but have not found it so far. It seems there are not many little black holes in the universe, which is a pity. As a black hole gives off particles and radiation, it will lose mass. This will cause the black hole to get smaller and to send out particles more rapidly. Eventually, it will get down to zero mass and will disappear completely. The particles and radiation that come out of a black hole are in general different from those that fell into the hole. One can therefore ask, what happened to the original particles that collapsed to form the black hole? And what happened to any astronauts or spaceships that fell into the black hole later on? It seems the answer is that they go off into a little baby universe of their own. A small, self-contained universe branches off from our region of the universe. This baby universe may join on again to our region of spacetime. If it does, it would appear to us to be another black hole, which formed and then evaporated. Particles that fell into one black hole would appear as particles emitted by the other black hole, and vice versa. sounds just what is required to allow space travel through black holes. You just steer your spaceship into a suitable black hole. It better be a pretty big one, or the gravitational forces will tear you into spaghetti before you get inside. You would then hope to reappear out of some other hole, though you wouldn't be able to choose where. However, there's a snag in this intergalactic transportation scheme. The baby universes that take the particles that fell into the hole occur in what is called imaginary time. Imaginary time may sound like science fiction, but it is a well-defined mathematical concept. It is time measured using what are called imaginary numbers. The use of imaginary time seems essential in order to formulate quantum mechanics and the uncertainty principle properly. It can be thought of as a direction of time that is at right angles to the ordinary, or real, time that we experience. In real time, an astronaut who fell into a black hole would come to a sticky end. He would be torn apart by the difference between the gravitational force on his head and his feet. Even the particles that made up his body would not survive. Their histories, in real time, would come to an end at a singularity. However, the histories of the particles in imaginary time would continue. They would pass into the baby universe and would re-emerge as the particles emitted by another black hole. Thus, in a sense, the astronaut would be transported to another region of the universe. However, the particles that emerged would not look much like the astronaut. Nor might it be much consolation to him, as he ran into the singularity in real time, to know that his particles will survive in imaginary time. The motto for anyone who falls into a black hole must be, think imaginary. What all this means is that going through a black hole is unlikely to prove a popular and reliable method of space travel. First of all, you would have to get there by traveling in imaginary time and not care that your history in real time came to a sticky end. Second, you couldn't really choose your destination. It would be a bit like traveling on some airlines I could name. Although baby universes may not be much used for space travel, they have important implications for our attempt to find a complete unified theory that will describe everything in the universe. Our present theories contain a number of quantities, like the size of the electric charge on a particle. The values of these quantities cannot be predicted by our theories. Instead, they have to be chosen to agree with observations. However, most scientists believe that there is some underlying unified theory that will predict the values of all these quantities. There may well be such an underlying theory. Many people think it is the theory of superstrings. This does not contain any numbers whose values can be adjusted. One would therefore expect that this unified theory should be able to predict all the values of quantities, like the electric charge on a particle, that are left undetermined by our present theories. Even though we have not yet been able to predict any of these quantities from superstring theory, many people believe that we will be able to do so, eventually. However, if this picture of baby universes is correct, our ability to predict these quantities will be reduced. This is because we cannot observe how many baby universes exist out there, waiting to join onto our region of the universe. There can be baby universes that contain only a few particles. These baby universes are so small that one would not notice them joining on or branching off. However, by joining on, they will alter the apparent values of quantities, like the electric charge on a particle. Thus, we will not be able to predict what the apparent values of these quantities will be, because we don't know how many baby universes are waiting out there. There could be a population explosion of baby universes. However, unlike the human case, there seem to be no limiting factors, such as food supply or standing room. Baby universes exist in a realm of their own. It is a bit like asking, how many angels can dance on the head of a pin? For most quantities, baby universes seem to introduce a definite, although fairly small, amount of uncertainty in the predicted values. However, they may provide an explanation of the observed value of one very important quantity, the so-called cosmological constant. This is a quantity that would give the universe an inbuilt tendency to expand or contract. On general grounds, one might expect it to be very large. Yet we can observe how the expansion of the universe is varying with time and determine that the cosmological constant is very small. Up to now, there has been no good explanation for why the observed value should be so small. However, having baby universes branching off and joining on will affect the apparent value of the cosmological constant. Because we don't know how many baby universes there will be different possible values for the apparent cosmological constant. However, a nearly zero value will be by far the most probable. This is fortunate, because it is only if the value of the cosmological constant is very small that the universe would be suitable for beings like us. To sum up, it seems that particles can fall into black holes, which then evaporate and disappear from our region of the universe. The particles go off into baby universes, which branch off from our universe. These baby universes can then join back on somewhere else. They may not be much good for space travel, but their presence means that we will be able to predict less than we expected, even if we do find a complete unified theory. On the other hand, we now may be able to provide explanations for the measured values of some quantities, like the cosmological constant. In the last few years, a lot of people have begun working on baby universes. I don't think anyone will make their fortune by patenting them as a method of space travel, but they have become a very exciting area of research. Thank you for your patience listening to my computer voice. That is all.
The ushers will hopefully collect the questions. Now you can pass them out to the aisles if you have. We'll do that, and I will take one question from someone who can get to a microphone. There's one over here, one over there, and there's one up there. Start. Any bold person here? I can't see, so forgive me. I'll take a question from anywhere if you want to do it. You bold. Go ahead.
Dr. Hawking, if...
Wait a minute, wait, we got a question coming from down here, so just a minute.
All right.
Okay, the question was, I didn't understand what you meant by imaginary time. Good luck, right? Okay, so he'll go ahead and it'll take him a minute to do that. He's got the backpack on the chair. There is a Toshiba 1200 XE. I think it's an XE, and that's what feed. And then there's a special customized board, which is the speech synthesizer, and that all hooks in. Right now he has a screen in front of him where it goes through. He's explained a little bit of it, and it's going down, and he picks the words off there, and he'll construct the sentence for us. Just talk amongst yourselves. I'm not going to talk through this, so we'll just wait, and then he'll let us know when he has the answer. And you're going to give me some answers here.
That's the reason I want to do some research in that.
That's kind of a funny one. to do with. Good. We're just going to read something. Okay. You want to write it down for me? Or you already did? Just write it down. You got a pen?
Can you some more there? Or do you want to sort out some that maybe just strike cards without any questions?
Well, some will be, but there's a merging of black holes one. You want to, one pulled into the other. It was pretty good.
There's 4 pretty good ones there.
God questions.
Yeah, well, probably good to ask one God one, because
just ask one good one.
No, one about God at least.
Yeah,
because
everybody wants to.
Yeah, exactly.
So we'll pull out a few God ones. I have some here. You have several God ones there.
Those are all good ones. So if you choose.
Are they all guide questions?
No, those are all good ones.
Well, I'm going to leave you. I mean, we'll worry about that. Let him answer the first one, then we'll pick. You pick one best one.
Well, choose the next one now. That's a good.
You go ahead and do that, because you're going to read it. Okay? You can do that. I'll say something like, I've asked Jonathan to read the next question. Incidentally, this microphone's on, so I don't know how much they will hear.
Answer.
That's great. You read the next one.
A lot of people who read my book also didn't understand about imaginary time. I now realize I should have explained it better. You can think of ordinary, real numbers as a horizontal line with 0 in the center, positive numbers on the right, and negative numbers on the left. Then you can think of imaginary numbers as a vertical line with 0 again at the center, positive imaginary numbers in the up direction, and negative imaginary numbers down. So they are a new kind of number at right angles to ordinary numbers. Imaginary time is just time measured with imaginary numbers instead of real numbers. So it is a kind of time at right angles to ordinary time.
Okay, one of the common questions that quite a few people have asked, and Richard Jones in particular, is our universe a baby or a parent?
Repeat it again.
Is our universe a baby or a parent?
Our universe is a parent universe, with baby universes leading off from it at black holes. There will also be much smaller baby universes leading off it, which we don't notice dawning on.
Okay, it's another common question, and it's how likely do you believe in life on other planets?
I have a whole lecture on that, but I won't give it now. I feel the universe is so big, there ought to be life somewhere else. But intelligent life cannot be very common, or we would have been visited by aliens.
Another common question. Obviously a lot of you think the same. In your opinion, will the universe expand forever, or at some time begin to collapse back onto itself?
Not quite jumping over. They are trying to define that there's something. You can ask all these.
I shall answer. I also have a lecture on that. In my opinion, the universe will continue to expand for many billions of years. But eventually it will collapse to a big crunch, which will be an end of time. I don't expect to be around at the time to be proved wrong.
What do you say, class?
He doesn't expect to be around at the time to be proved wrong.
This is going to be the last question. There were a lot of them of this along these lines, so I've kind of tried to formulate it simply. What was the role of God in the creation and/or design of the universe?
That is a big question. It is not for me to say.
Is that it? You're going to have to unplug him. Yeah. You'll have to unplug him.